Welcome to the 2008 Karl Terzaghi Lecture. The presentation of the Karl Terzaghi Lecture is one of the most important events of the Geo-Institute year, and on behalf of the Geo-Institute, I would like to welcome you this afternoon. I believe we have some past recipients of the award in the audience with us today. Would you all please stand and be recognized? Thank you. We are also honored today to have with us the Consul General of France in New Orleans, the Honorable Olivier Brochenin. And right now it's my pleasure to bring to the podium past president of ASCE, Bill Marcuson.
Instituted by the ASCE Board of Direction in 1960, the Terzaghi Lecture was established by the Soils and Foundations Division, now the Geo-Institute. Annually, the Geo-Institute Board of Governors recommends a distinguished engineer to deliver the Terzaghi Lecture. The 44th Terzaghi Lecturer is Dr. J.P. Giroud. He's with J.P. Giroud, Inc. now, but he's also the Chairman Emeritus and founder of Geosyntec Consultants. Our speaker tonight certainly has shown the expertise, innovation, and commitment to match the example set by Karl Terzaghi and the other distinguished lecturers who have received this renowned lectureship. I'd ask Dr. Giroud to join me at the podium now. And this says, this is to recognize that Dr. Jean-Pierre Giroud, PhD, member ASCE, has been awarded the Karl Terzaghi Lecture in recognition of your pioneering work and leadership in the development of the field of geosynthetics engineering and associated contributions to civil and geotechnical engineering. Authorized by the Board of Direction and signed Patrick J. Natal and David G. Mungan.
Thank you.
The check that goes with this will be mailed to you. I very much look forward to your lecture tonight, which is entitled Criteria for Granular and Geotextile Filters. And I personally want to thank you for your leadership to our profession. And I'd now like to turn the program back over to Art.
Thank you, Bill. And thank you, Dr. Giroud, for accepting our invitation to present the lecture tonight. I know how much effort it takes to prepare this type of a lecture. I know you've been traveling with your wife to another conference recently. We appreciate the effort. We're all very happy to be here, and we're glad you're here with us, too. Dr. Giroud was educated in France, receiving his PhD in 1974 in geotechnical engineering from the University of Grenoble, and he taught there as a professor of geotechnical engineering. He later served as the director of the Geotextiles and Geomembranes group of Woodward Clyde Consultants. In 1983, he founded Geosyntec Consultants. In 2001, he retired from Geosyntec as chairman emeritus and established J.P. Giroud, Inc. Dr. Giroud is one of the founding members of the International Geosynthetic Society and served as its president until 1990. He is chairman of the editorial board of the journal Geosynthetics International and was chairman of the editorial board of the journal Geosynthetics and Geomembranes for 10 years. He chaired both the second annual conference on geotextiles and the International Conference on Geomembranes. He also has chaired the Technical Committee on Geosynthetics of the International Society of Soil Mechanics and Geotechnical Engineering. Dr. Giroud has presented numerous prestigious lectures, including the Vienna Terzaghi Lecture in 2005 and the 2005-2006 Mercer Lecture Series. In 1996, he presented the keynote lecture of the second Geofilters Conference in Montreal. Dr. Giroud has been honored by his colleagues and peers. He was recognized as a hero of the profession by the Geo-Institute in Austin in 2005. When he was elected as an honorary member of the IGS in 2002, he was pronounced as truly the father of the IGS and the geosynthetics discipline. In 1994, the IGS named its highest award the Giroud Lecture in recognition of his invaluable contributions to the technical advancement of the geosynthetics discipline. In 2007, Dr. Giroud was appointed Doctor Honoris Causa of the Technical University of Bucharest, Romania. Since 1963, Dr. Giroud has been a prolific author with over 250 papers on geosynthetics and an additional 100 papers on other geotechnical topics. In addition, he's the author of the Geosynthetics bibliography. Recently, Dr. Giroud wrote the chapter on filter criteria in the book commemorating the 75th anniversary of Terzaghi's book, Erdbaummechanik. He has also published valuable state-of-the-art reviews of granular and geotextile filters and the use of geosynthetics in dams and many others. Dr. Giroud is a pioneer in the field of geosynthetics. He's recognized throughout the world as a geosynthetics leading expert. In 1977, he coined the words geotextile and geomembrane. Dr. Giroud was the originator of a number of geosynthetic applications, such as the first non-woven geotextile filter, the first geotextile in a dam, the first geotextile cushion for a geomembrane, the first double liner using geomembranes, and the first entirely geosynthetic double liner system with 2 geomembranes and a geonet leakage detection system. Dr. Giroud has developed methods for the design of geosynthetic liner systems and drainage systems for use in landfills and other facilities, and he has authored 3 books in the area of geosynthetic liner systems. Much of his work has been incorporated into ASTM and other standards. He's worked extensively with the US EPA, the FHWA, the US Bureau of Reclamation, performing research, providing consulting services, and preparing and presenting numerous short courses. Over the past 40 years, Dr. Giroud has developed many of the design methods used in geosynthetics engineering today. The design of filter and drainage systems, liner systems, reinforcements, the evaluation of environmental factors on geosynthetics are all influenced to this day by the design methods that he has developed. Dr. Giroud's lifelong commitment to the advancement of the geosynthetics discipline and his contributions to the profession are clear indications of his qualifications to present his lecture titled Criteria for Granular and Geotextile Filters. Ladies and gentlemen, I present to you the 2008 Terzaghi Lecturer, Dr. Jean-Pierre Giroud.
Thank you for this introduction. 3 years ago, I was very honored to present the Vienna Terzaghi Lecture in Austria. I was using the lectern from where Karl Terzaghi had presented the consolidation theory 80 years before. The historic presentation by Terzaghi was dramatic. One of the attendees who had disagreed with him committed suicide. Feel free to do so if you disagree with me. I never met Karl Terzaghi, and my closest association to him was 20 years ago when I presented a seminar on filters. At the end of my presentation, an old geotechnical engineer came to me and said, "You remind me of Karl Terzaghi." I replied that I was very flattered and asked why he was saying that. And he said, "I saw Terzaghi once, and like you. He was talking about filter criteria with a European accent. Tonight, ladies and gentlemen, dear colleagues, I will talk about filter criteria with a European accent. Work on filter criteria has been published by many authors, and it is not possible to present all of this work in a lecture. In fact, I will only present work that I have done. This doesn't mean that I ignore work done by others, but I had to limit the scope. The work I've done on filter criteria is essentially theoretical. This does not mean I ignore experimental work. In fact, I do refer to experimental data, but by just doing rational analysis, it was possible to build a coherent system of filter criteria. And I want to present the development of this coherent system because it provides an opportunity to better understand the mechanisms of filtration. And this coherent system has many practical applications, and I want to make geotechnical engineers aware of these possibilities. I did this work to improve criteria for geotextile filters, but this work is applicable to granular filters. In fact, the first steps of the development of criteria for geotextile filters were inspired by granular filter criteria. As a result, this lecture often refers to Terzaghi's filter criteria. All the work I have done on filter criteria was done with a pen and a piece of paper, or perhaps several pieces of paper. And my work and this lecture do not involve complex mathematics and extensive use of computers. As a result, my work is easy to understand and easy to use, and this lecture should be easy to follow. Granular filters are well known, so let's see a few examples of geotextile filters. A geotextile filter in a drainage trench, in a landfill, in a dam. Now, Terzaghi's criteria for granular filters are well known. The D15 of the filter should be greater than 4 or 5 times the D15 of the soil. That means the D15 of the filter must not be too small, and this is the permeability criteria. The D15 of the filter must be less than 4 or 5 times the D85 of the soil. That means the D15 of the filter must not be too large, and this is the retention criterion. The difference between the factors 4 or 5 is not significant, and I will use 5 in my discussions. Both Terzaghi's criteria are expressed using the D15 of the granular filter. This is possible because the D15 of a granular material is related to the size of its openings. And the relationship is opening size is 1/5 of the D15 of the filter approximately. And this is based on theoretical and experimental work on arrangements of particles. In the 70s, several criteria for filter fabrics were used, some of them inspired by Terzaghi's criteria. Here is an example of criteria used in the 70s. In particular, the opening size of the filter had to be smaller than the D85 of the soil and greater than 0.15 millimeters. Early on, it was even explicitly mentioned that non-woven filter fabrics should not be used. In any case, many non-woven fabrics were eliminated by the requirement of opening size greater than 0.15 millimeters, and all were eliminated by the requirement that the open area should be less than 36%. Progressively, the anti-non-woven clauses disappeared. However, the remaining criteria for filter fabrics were not completely satisfactory, as we will discuss. And then in 1977, the terminology geotextile appeared, and it will be used in the rest of this lecture. In this lecture, I will discuss problems related to the old criteria, present the development of proposed criteria, and discuss the application of the proposed criteria to both geotextile filter and granular filters. First, the development of a permeability criterion for geotextile filters with applications to granular filters. The presence of a filter disturbs the flow of water in the soil upstream of the filter. So the selected filter must be such that the disturbance is small and acceptable. The disturbance can affect pore pressure and flow rate. Therefore, the permeability criterion should include two requirements, one for pore pressure and the other for flow rate. So first, the pore pressure requirement. The presence of a filter potentially increases the pore pressure in the soil upstream of the filter. So the selected filter should be such that the pore pressure increase is as small as possible and ideally zero. Here is the curve of water pressure as a function of depth for water flowing through a soil layer without a filter. Now, if we consider the case with a filter behind the soil, we can see that there is an excess pore pressure as shown here. Now, this excess pore pressure decreases if the hydraulic conductivity of the filter increases until we reach the point where there is no excess pore pressure. And the analysis of this diagram shows that the presence of the filter causes no pore pressure increase if the hydraulic conductivity of the filter is greater than the hydraulic conductivity of the soil multiplied by the hydraulic gradient in the soil next to the filter. A typical hydraulic gradients in soils next to filters are shown here, and they are typically less than 2 with the exception on filter associated with clay liners. Let's discuss now the second requirement, which is the flow rate requirement. The presence of a filter, even very permeable, decreases the flow rate compared to the case without filter. Calculations done with Darcy's equation show that the flow rate decrease is less than 10% of the flow rate without filter if the following requirements are met. Hydraulic conductivity of filter greater than hydraulic conductivity of the soil if the filter is thin, 1 to 10 millimeters, and hydraulic conductivity of the filter greater than 25 hydraulic conductivity of the soil for a thickness of the order of 250 to 2500 millimeters. Of course, the thickness applies to geotextile filters. Therefore, the first requirement reads hydraulic conductivity of the filter greater than hydraulic conductivity of the soil for geotextile filters. And the second requirement applies to granular filters, and therefore it reads hydraulic conductivity of the filter should be greater than 25 times the hydraulic conductivity of the soil in the case of granular filters. Let's discuss those two requirements. In the case of geotextile filters, the flow rate requirement is less stringent than the pore pressure requirement when the hydraulic gradient is greater than 1, and the opposite, of course, when the hydraulic gradient is less than 1. With granular filters, 25 times the hydraulic conductivity of the soil is virtually always more stringent than the pore pressure requirement because the gradient is virtually always less than 25. Now, it's important to note that this flow rate requirement for granular filters can be expressed in terms of particle size. Indeed, it is well known that the permeability of a granular material is proportional to the square of a small particle size, D10, D15, for example. This is the well-known Kozeny-Kármán's equation, of which Hazen's equation is a special case. Therefore, the flow rate requirement for a granular filter is equivalent to D15 of the filter greater than 5 times the D15 of the soil. Of course, this is the classical permeability criterion for granular filters. So this discussion shows that the classical permeability criterion for granular filters is only the flow rate requirement and not the pore pressure requirement. But generally, it is more stringent, so it is not a problem. So in conclusion, for the permeability criterion, the permeability criterion for geotextile filters is either Ks multiplied by the gradient or Ks, depending on the gradient, whichever is greater. But for granular filters, it is generally 25 times the hydraulic conductivity of the soil, which is the traditional permeability criterion. So therefore, there is a difference between granular filters and geotextile filters regarding the permeability criterion. In the case of geotextile filters, either the pore pressure requirement or the flow rate requirement governs, whereas in the case of granular filters, it is virtually always the flow rate requirement that governs. So clearly, to develop an appropriate permeability criterion for geotextile filters, it would have been incorrect to simply imitate Terzaghi's permeability criterion for granular filters, because we would have seen only one of the two requirements. So Terzaghi's permeability criterion, which is of course correct for granular filters, provided a starting point for the derivation of a permeability criterion for geotextile filters. However, to extend the work of Terzaghi on granular filters to geotextile filters, it was necessary to thoroughly understand the requirements related to water flow through a filter. Let us discuss now the development of retention criterion for geotextile filters with applications to granular filters. The question is, how should we select the maximum allowable opening size of a geotextile filter to retain a soil? A simple answer would consist in adapting to geotextiles Terzaghi's retention criterion for geotextile filters, which is for granular filters, which is D15 of the filter less than 5 times D85 of the soil. We know that the opening size of a filter is about 1/5 of the D15 of that filter. Combining the two equations gives opening size of the filter less than D85 of the soil. This equation means that a filter should only retain the large soil particles. Retaining large soil particles works if the large particles retain smaller particles. In other words, if the soil is internally stable. Therefore, an ideal retention criterion should take into account not only the opening size of the filter, but also the internal stability of the soil. However, to a certain degree, granular filters may work even if the soil is not internally stable because they are thick. And the mechanism is the following. Particles that are not retained may accumulate in the filter, thereby decreasing the filter opening size until the filter works. In other words, a granular filter adapts itself to the soil to a certain degree. As a result, a granular filter can be designed to a certain degree using a retention criterion, such as Terzaghi's retention criterion, that does not take into account the internal stability of the soil. Essentially, granular filters, because they are thick, can be designed using a simple retention criterion, such as Terzaghi's retention criterion. However, this is true only to a certain degree, which limits the applicability of Terzaghi's retention criterion to soils having a maximum particle size of 4.75 millimeter, hence the practice of the truncation of the particle size distribution curve, which we will discuss later. Now, while granular filters benefit to a certain degree from their thickness, geotextile filters are thin, which has created an incentive for developing more accurate retention criterion. A criterion that takes into account the internal stability of the soil. In internally stable soils, there are particles of a certain size that form a continuous skeleton. This continuous skeleton entraps particles that are a little smaller than the skeleton particles. In turn, these particles entrap particles that are a little smaller, and so on. So this is an internally stable soil. So therefore, if a filter has openings such that the skeleton is retained, then all particles smaller than the skeleton are retained in the case of an internally stable soil. And of course, particles larger than the skeleton particles will be retained, because if a filter retains certain particles, of course, coarser particles will be retained. But if a filter has openings too large to retain the skeleton, the soil is not retained because the particles that are retained in this case do not form a continuous skeleton. So therefore, a filter must have openings such that the skeleton is retained. So that leads to two questions. What is the size of the skeleton particles? And what filter opening size is required to retain a given skeleton? So let's address the first question. As mentioned earlier, the skeleton is an essential consideration for the retention of an internally stable soil. Internal stability depends on particle size distribution, which is characterized by the coefficient of uniformity. So geometric considerations show that in a soil with a coefficient of uniformity of approximately 3, particles are tightly interlocked. In other words, such a soil has maximum internal stability. This is illustrated in the following slides. When a soil has a coefficient of uniformity equal to or less than 3, the coarser particles form a continuous skeleton that entraps all other particles. But if a soil has a coefficient of uniformity greater than 3, the coarser particles are not in contact, and they do not form a continuous skeleton that entraps other particles. In other words, when a soil has a coefficient of uniformity greater than 3, the coarser particles float in the matrix formed by the other particles, and as a result, they do not contribute to internal stability. So, in the case of a soil having a coefficient of uniformity greater than 3, to develop a retention criterion that takes into account internal stability, we will only consider the fraction of the soil that has a coefficient of uniformity equal to 3. In other words, we ignore the coarse fraction in the development of the retention criterion. This means that we truncate the particle size distribution curve and consider only the particles smaller than Dmax, shown here, such that the remainder of the curve has a coefficient of uniformity of 3. Now, the user of the proposed retention criterion does not have to do this truncation. The truncation is done automatically. It is included in the equations that express the retention criterion. So only this fraction of the curve with a coefficient of uniformity of 3 is used in the proposed retention criterion. So we answered the first of the two questions, the size of the skeleton particles. Now, what filter opening size do we need to retain a given skeleton? If a soil is in a loose state, represented by a cubic arrangement, particles pass if the opening size is just larger than the particle size. But if the soil is in a dense state, represented by an hexagonal arrangement, particles do not pass if the opening size is just larger than the particle size, because there is the formation of a stable bridge. So if the soil is in a dense state, particles pass only if the opening size is twice as large as particle size. So based on this demonstration, the internal stability of a soil depends not only on its coefficient of uniformity, as we discussed before, but also on its density. So far in this lecture, the presentation of the retention criterion has been mostly qualitative, but I have done a mathematical analysis of the role of the coefficient of uniformity and the density of the soil, and calculations, not presented here, lead to the following equations. So we see here the influence of soil density, and we see here the influence of coefficient of uniformity. In reality, in those equations, I use the linear coefficient of uniformity rather than the traditional coefficient of uniformity for the simplicity of equations. So all geotechnical engineers know the definition of the coefficient of uniformity. The linear coefficient of uniformity is defined using a straight line that closely follows the central part of the actual particle size distribution curve, as you see here. So the equations that I just showed can be represented graphically with a graph of the maximum allowable opening size divided by the D85 of the soil as a function of the linear coefficient of uniformity. And we can see that all these curves have a maximum for the most stable soil, which is the soil with a coefficient of uniformity of 3. Now, the horizontal dashed line represents Terzaghi's retention criterion expressed in terms of opening size, and of course, it does not depend on the coefficient of uniformity of the soil. So there is a big difference between the two criteria, and in particular, using the red line, which is Terzaghi's criterion, rewritten in terms of opening size, for soils having a large coefficient of uniformity, allows filter openings that are way too large, hence a risk of piping. So therefore, a geotextile filter is safer if it is designed with a retention criterion that takes into account the internal stability of the soil. But we can do the same for granular filters. The retention criterion developed, as we have seen for geotextile filters, can be extended to granular filter. And here, the vertical axis, instead of being opening size, is D15 divided by D85 of the soil, just to be consistent with the traditional practice for granular filters. And we see here values greater than 5 for the ratio D15 of the filter divided by D85 of the soil, but this is consistent with experiments by Bertram, Sherrard, and others. And again, for large coefficient of uniformity, we can see that Terzaghi's criterion is not conservative. An important consideration is that this retention criterion is applicable regardless of maximum particle size. In other words, it is not limited to particles smaller than 4.75 millimeter. Therefore, the need for the tedious operation of truncating particle size distribution curves at 4.75 millimeters is eliminated. In fact, with the proposed retention criterion, there is truncation, but it is done automatically. In other words, it is included in the equations, but more importantly, the automatic truncation takes place at the appropriate location, which is generally not 4.75 millimeters. So therefore, by extending to granular filters, the retention criterion developed for geotextile filters, we have obtained a tool for designing granular filter that is simpler and safer than the traditional criterion for soils having a large coefficient of uniformity. So far, we have discussed the use for geotextile filters of the two criteria used for granular filters, the permeability criterion and the retention criterion. But two other criteria are needed for geotextile filters. Indeed, since there is an almost unlimited possibility of making new materials in geosynthetics manufacturing, it is possible to imagine extreme geosynthetic materials that would be or could be unlikely to perform properly as filters, such as geosynthetics with very few openings or some extremely thin geosynthetics. So we need criteria to prevent the use of such materials as filters. So we need, therefore, two additional criteria. One, to ensure that the number of openings is sufficient, and a criterion to ensure that filter thickness is sufficient. First, let's discuss the criterion for the number of openings. In addition to having adequate opening size, a filter should have as many openings as possible per unit area. Indeed, if the number of openings is small, the performance of the filter may be adversely impacted. Liquid flow is concentrated in a small number of channels, which increases the risk of erosion, increases particle transport, thereby increasing the risk of clogging. And if the number of openings is small, clogging only a few of the openings may significantly reduce flow capacity. So it should be noted that geotextiles are so permeable that even if a geotextile has a small number of openings per unit area, it may still meet the permeability criterion. So clearly, the permeability criterion is not sufficient to eliminate geotextile filters that do not have enough openings. Therefore, a criterion specific to the number of openings per unit area is needed. Calculations show that the number of openings per unit area is given by the first equation for woven geotextiles, where AF is the relative open area of the woven geotextile, and the second equation for non-woven geotextiles, where N is the porosity of the non-woven material. Now, the relative open area of a woven geotextile is in fact the two-dimensional equivalent of porosity. This is obviously true geometrically, but it's confirmed by the fact that open area in the equation for woven geotextiles play the same role as porosity in the other equation. So therefore, both relative open area for a woven geotextile and porosity for a non-woven geotextile, or even a granular material, can generically be called the porosity of a filter material. So essentially, the two equations become one, and They mean that the number of filter openings is proportional to the porosity of the filter regardless of the type of filter. So in other words, regarding the required number of openings per unit area, all types of filters should be treated in the same way, and the governing parameter is the porosity of the filter material. Now, I do not know a rational analysis of the required number of openings or the required porosity of a filter. The only available guidance I know is that we know that granular filters work, and we know that their porosity is of the order of 0.3, almost always greater than 0.2. Therefore, it is reasonable to adapt the following porosity criterion for all filters. Porosity should be greater than 0.2, that is 20%. Now, this porosity criterion has never been formulated for granular filters because they all have approximately the same porosity. But it is essential for geotextile filters because there is a wide range of porosity from 1% to more than 90% for non-woven geotextiles. All non-woven geotextiles, even compressed, meet easily the porosity criterion. But many woven geotextiles have a low relative open area, which is the equivalent of porosity. However, some of them are still used as filters. But based on the analysis, woven geotextiles with a relative open area less than 20% should not be used as filters. Let's discuss the second of these new criteria needed for geotextile filters, the criteria related to thickness. And in this discussion, I will not consider woven geotextile filters because the thickness is a special consideration in this case. So I will only discuss non-woven geotextile filters and granular filters. To understand the role of filter thickness, it is necessary to understand how a soil particle travels through a filter. A soil particle that travels through a filter, any filter, granular or non-woven geotextile, must go through narrow passages called constrictions. In the case of a geotextile filter, a constriction is a passage between fibers. And the size of a constriction is the diameter of the largest spherical particle that passes through the constriction. Now, a soil particle that travels through a filter moves from one constriction to another, thereby following a filtration path. The particle will be stopped or will pass depending on the size of constrictions in that particular filtration path. Here is the cross-section of a geotextile filter. The fibers are black, the particles are blue here. Now, particles can be stopped on top, such as the red one, or inside, such as the yellow ones, or pass, such as the green particles. Now, let's consider the non-woven material used to make a geotextile filter, a non-woven geotextile filter. This material is characterized by a constriction size distribution curve, shown here. And an important point, as we will see, is the smallest constriction. The constriction size distribution curve is a characteristic of the material the geotextile is made from. It is not a characteristic of the geotextile. A geotextile with a given thickness is characterized by another curve, which is the opening size distribution curve, shown here. So why do we have a curve and not a single value of the opening size as we have in granular filters? Let's discuss that. Each filtration path contains a number of constrictions. A soil particle can go through the filter if it is smaller than the smallest constriction in the path. So therefore, each filtration path is characterized by the smallest constriction in that path. Thus, the smallest constriction in a given path is the opening size of that filtration path. In general, the smallest constriction is different in different filtration paths. So therefore, each filtration path has a different opening size. So this is why we have an opening size distribution curve, shown here again. And naturally, the maximum opening size for all filtration paths is the opening size of the filter, which is, of course, at the top of the opening size distribution curve. So now we have two curves. So what is the relationship between these two curves? The opening size distribution curve, which characterizes a filter with a given thickness, and the constriction size distribution curve, which characterizes the material used to make the filter. So we need to make some geometric considerations to establish this relationship. In a filter, there is a very large number of filtration paths, millions per square meter. But in a non-woven geotextile filter, due to the limited thickness, there are not many constrictions in each filtration path, typically 10 to 100. So statistically, it's very different, 1 million or 10 to 100. So statistically, the conclusion is the smallest filtration path opening size is the smallest constriction size, but the largest filtration path opening size is not the largest constriction size. Accordingly, the two curves have the same origin, but not the same top. So this conclusion, based on statistics, may seem too quick, but it becomes easy to understand if we consider two limit cases. First limit case, if a filter has a quasi-zero thickness, there is only one constriction per filtration path. Therefore, the opening size distribution curve is the same as the constriction size distribution curve. So this is what we get. Second limit case, if a filter has infinite thickness, the probability for having the smallest constriction in every filtration path is 100%. As a result, all the filtration paths have the same opening size, which is the smallest constriction size. Therefore, in this case, the opening size distribution curve is a vertical line, as we see here. Typical non-woven geotextiles are between the two limit cases. So here we see a thick non-woven geotextile, you see a thinner material. They are between the two extreme cases. Now, for filters made of the same material, characterized by its constriction size, distribution curve, the opening size increases with decreasing thickness, as we saw in the preceding graph. Okay? So the important conclusion is that for a given material, the opening size of a filter made from this material depends on the thickness of the filter. And we just saw that, in fact, it decreases for increasing values of the thickness of the filter. This is true for all types of filters. But from a practical standpoint, there is a major difference between geotextile filters and granular filters. Granular filters have a quasi-infinite thickness. So therefore, they have a unique opening size, as we just demonstrated. Now, so far in this lecture, the impact of geotextile thickness on opening size has been discussed qualitatively. But I have done a mathematical analysis and obtained a relationship between geotextile opening size and geotextile thickness. This is the equation, and parameters are the fiber diameter and the porosity of the geotextile. This relationship is represented by a family of curves, and for non-woven geotextiles, as I said before. Now, consistent with what we have just discussed, we see on the graph that for a given porosity, which is for a given non-woven material under a given normal stress, the geotextile filter opening size decreases for increasing values of the geotextile thickness. So these quantify what we showed before qualitatively. The same analysis leads to another equations for the number of constrictions through a non-woven geotextile filter. This is the equation. So we can calculate the number of constrictions. A parametric study of the curves on this graph has shown that beyond a geotextile thickness that contains approximately 25 constrictions, the opening size is not significantly affected by changes in geotextile thickness. And here is the zone of the graph, and the separation is almost a straight line with more than 25 constriction, and indeed we see that the slope of the curves is very flat, which indicates not a great influence of thickness. So therefore, to be reliable, a non-woven geotextile filter should have a thickness of at least 25 constrictions. This is the thickness criterion. Now, it's convenient to express thickness in terms of numbers of constriction, so the criterion is independent of porosity, fiber diameter, etc. This work, by the way, is the basis for an ASTM standard on filtration. In summary, 4 filter criteria have been established for geotextile filter: permeability, retention, porosity, and thickness. But there is a last question. Is this complete? Well, filtration is governed by filter openings. The characteristics of filter openings are the size, the shape, the density, which is the number per unit area, and the distribution. The 4 criteria address 3 of those characteristics, as we have seen, the size, the density, and the distribution. But we did not address the shape in those 4 criteria. The shape of filter openings is likely to be a minor consideration for granular and non-woven filters due to the random structure. But in contrast, the shape of openings may be a relevant issue in the case of woven geotextiles or other types of man-made fibers. So clearly more work is needed on the impact of shape on filter openings, on the performance of filters. But in the meantime, we can consider that the set of 4 criteria is complete, at least for granular and non-woven filters. Furthermore, this set of 4 criteria is a coherent set of criteria because it addresses only parameters that are relevant to the filtration function. Other types of requirements for geotextile filters, such as strength requirements, durability requirements, are sometimes presented as part of geotextile filter criteria. These are not filter criteria because they are not intrinsic to the filtration function. They can be used for geotextiles performing any other function. And to conclude, I will present a case history, the first geotextile filter in a dam. In 1989, this dam was on the cover of Civil Engineering. Almost 20 years before, it had been the first dam constructed with geotextiles. Geotextiles on the upstream slope, as you see on this photo, but more importantly, geotextiles inside the dam, geotextile filter for the downstream drain of the dam. This is a photo taken during construction of the downstream portion. You see here where approximately will be the embankment of the dam. We see here a downstream drain with geotextile filter and gravel in the trench, and being constructed finger drains on the side connected to the downstream drain, also equipped with geotextile filter. It is a 17-meter high homogeneous dam constructed with silty sand. I was the design engineer for the dam, and I could not get adequate sand filter at the last minute. I had to make a quick decision. I elected to use a non-woven geotextile, never used before as a filter. That was in 1970. The dam has been constructed and has been in service ever since 1970. The performance has been satisfactory, constant trickle of clean water, flow rate measured at the outlet consistent with the hydraulic conductivity of the embankment soil, no seepage of water ever observed through the downstream slope, and geotextile filter in good condition, in particular with negligible clogging, 0.2% of the pore volume, as demonstrated by test on samples of geotextiles removed from the actual filter 6 years and 22 years after construction. So the outstanding performance of the geotextile filter can be explained today. The first comment I will make is that fortunately the filter was not designed using classical filter criteria. In reality, I have to confess that I did not use filter criteria to select the geotextile filter. I selected the geotextile on the basis of limited experimental data available at that time. Therefore, some degree of luck was involved in the success of this filter, and this is why I'm here today. 10 years later, in the 80s, I felt compelled to repay for that luck and started working on filter criteria. So today, we can finally use the filter criteria for this dam. We have no time, so I just say that it is easy to check that the permeability, porosity, and thickness criteria were met, and we will only discuss the most important, the retention criteria. This is the particle size distribution curve of the soil used in the dam. Coefficient of uniformity, 90. Linear coefficient of uniformity, 53. Use of Terzaghi's retention criterion on the full curve, we obtain 6.4 millimeter. This is very large. We would not use that to retain a silty sand. Well, of course, the problem is caused by the large coefficient of uniformity. So we do what all geotechnical engineers do, truncate the curve. This is the truncated particle size distribution curve. Apply Terzaghi's criterion and obtain 1.8 millimeter. Still very large. We should not use that to retain a silty sand. One may object that I use retention criteria for cohesionless soil, whereas we had 30% of particles smaller than 0.075 millimeter. So I used Giroud criteria and obtained 2.7 millimeter. This is still large. I reused Giroud's criteria on the truncated particle size distribution curve, 0.8 millimeter, still very large. This soil seems to defy all retention criteria. So let's try to use the proposed retention criterion. This is the relevant equation for this case, taken from the table I showed before. Used it for the particle size distribution and obtained 0.135 millimeter. Let's try to use it for the truncated particle size distribution curve, and we find the same result. Well, we should not be surprised because I said that truncation is automatically included in the retention criteria. So this is why we obtain the same result. So this remarkable result confirms the validity of the proposed criterion. In conclusion, the required value of for the opening size of the filter was 0.135 millimeter. This seems more reasonable than the larger values that we obtain with other criteria. The measured opening size on samples taken from the dam was 0.1 millimeter. Interestingly enough, with one of the equations I presented before, we can also calculate opening size from fiber diameter, porosity, etc., and we obtain 0.099 millimeter. So, therefore, the retention criterion is met here. So in conclusion, the geotextile filter performed well since construction. The 4 criteria are met, which is consistent with the good performance. In summary, we have reviewed the 2 classical filter criteria, the permeability criterion and the retention criterion, for both granular and geotextile filters. We have added 2 criteria for geotextile filter, the porosity criterion and the thickness criterion. The conclusion for geotextile filters is that the 4 proposed criteria for geotextile filters form a coherent set of criteria that allow safe design of geotextile filters. And the conclusion for granular filter is that the retention criterion for granular filters can be improved based on developments made for geotextile filters. Therefore, what started as technology transfer from geotechnical engineering to geosynthetics engineering has resulted in technology transfer from geosynthetics engineering to geotechnical engineering. I am sure that Terzaghi would have agreed that his famous filter criteria were not frozen forever, but rather could lead to new developments. I am sure Terzaghi would have agreed that with new filter material, the geotextile, it was not sufficient to adapt his criteria, but it was necessary to review the fundamentals of filtration and develop new criteria. So just imitating the great masters is not the best approach to solving modern problems. We do not have to do today what Terzaghi would have done 50 years ago. We need to do today what Terzaghi would do today. Thank you.
Would you like to take questions?
No, this is better.
Thank you, Dr. Giroud, for your excellent lecture. We're all very thankful that we don't have to rely on luck because we can follow the design criteria that you provide for us. Thank you. Thank you all very much for attending the Terzaghi Lecture this evening. Have a good evening.